Okay, we shall start. What? He's on? We are very happy to have Nima, just arrived. And he will tell us about positive geometry of effective field theory.
All right, guys, it's wonderful to be here. I know you guys are all going to go enjoy a well-earned sleep, or many of you, later this afternoon, so we'll try to entertain you before that. For many, many years now, I've been working on a collection of ideas that are sort of loosely associated with the words positive geometry and their connection with the physics of scattering amplitudes, cosmological correlators, and roughly speaking, all sorts of fundamentally dynamical processes, sort of not Euclidean questions, more Lorentzian questions. And I've tried to give summer school, winter school talks about it from time to time, and it doesn't really work so well. The ideas are incredibly simple, but they're somewhat unfamiliar. And so even if you have sort of 4 or 5 hours, you can sort of barely get going. So, but happily, somewhat to my delight, over the past year or so, very similar ideas at a much more elementary level. So not using all of the interesting structures that have shown up, but similar sort of versions of the same kind of ideas that show up in amplituhedra, associahedra, cosmological polytopes, all these fancy things, have shown up in much more down-to-earth familiar places in the context both of effective field theories and conformal field theories. I decided to give these lectures on the aspect of these things that have shown up in effective field theory. So think of this as a kind of aperitif or an appetizer to sort of get a peek into what some of these ideas are about. I should say if you are interested in the other stuff, which is sort of what I'm really obsessed about these days, what that subject really needs is a full-length graduate course, and I will actually finally be giving one of these things. I'm spending a sabbatical next year at the Center for Mathematical Sciences at Harvard, where I'll be running a program with a bunch of mathematicians on this general subject, and I'll also be teaching a systematic graduate course that the folks at Harvard are kind enough to put online. So if you're interested in learning more about that subject systematically, wait about a year from now, and hopefully there'll be something that'll give you a good entree into it. Anyway, so, but just I'll say one qualitative thing before getting started. Positivity, of course, has a lot, famously shows up in physics all over the place. And we normally think of positivity as a consequence of other things. Things are positive in physics essentially for two reasons. One, because energies are positive, and two, because probabilities are positive. So the positivity of probabilities and energies implies various things about physical observables, some obvious and some slightly less obvious. But from that point of view, it's a sort of causality, locality, causality, and unitarity that are king, and they imply certain positivity properties that we can go explore and learn about later. In a sense, what's happened in the story of positive geometries and scattering amplitudes and cosmology and all the rest of this stuff recently is a kind of an inversion of that story, that you see some kind of interesting positive structures that imply locality and unitarity and causality, at least in various toy models. And so that sort of gives you a feeling that there's more power to this positivity than you may have thought beforehand. It's not like that there is something more primitively positive that implies not only the positivities we're used to, but all sorts of other things besides. And so it's really from that experience that with Yutin Huang and Tutu Shuang, I should say that this is the new things I'll be talking about is actually work that has not yet appeared. But don't worry, this is going to be an extremely down-to-earth, elementary set of lectures. You should feel free to interrupt with any questions anytime. And the goal is to really get you to learn very specific, concrete, basic things, maybe a lot of things that perhaps used to be textbook material 40 years ago, but aren't textbook material typically anymore. But this, the systematic exploration of this subject will appear hopefully pretty soon. The delay is all my fault in a paper with Yutin Huang and Zhuchu Wang. But let me give a slightly earlier history of this, which is something that was, in a sense, repopularized around 15 years ago as a perhaps surprising implication of positivity for low energy effective field theories. And so let's begin with a simple example. So let's say you have a Lagrangian for a free massless scalar, and let's say the scalar has a shift symmetry, so all the interactions are derivative interactions, and so the first correction that you can have in the low energy effective action looks like that. Now, if you're a Wilsonian effective field theorist, that's it, you're done. And you can't really say anything about these coefficients unless you go and measure them from experiment. And otherwise, you naively don't expect that there's any constraints. But what a number of us pointed out around 15 years ago is that, in fact, causality / unitarity, and these things are very closely tied to each other, actually implies that these constants are positive. I might have to sign wrong here, but I will, which is a big deal when you talk about positivity. You know, there's something known as Schenker's theorem, after the great Steve Schenker, which is that thing you hate the most will next most be relevant for your research life, okay? And this is, this is something that you will learn the deep truth of as you grow in your physics career. But had anyone told me that, you know, in my 40s I'd be this anal person about signs, I would have looked at them like they were nuts. So, but anyway, here I am. I have to be careful about signs in my new life. Anyway, this is the only time I'm going to be loose about the sign, because we'll quickly switch to talking about more invariantly talking about these operators in terms of amplitudes in a second. But anyway, so what is the reason for this? Let's just back up for a second. If you're a model builder or a phenomenologist, you know that we're not really supposed to be able to, if you want to learn anything about higher dimension operators, you have to look for situations where they break a symmetry, right? After all, the leading interactions dominate low energy physics, and so if you want to look for some effect of very high energy physics, you have to find a process for which the high energy physics gives you, for which the universal, the two derivative interactions at long distances give you 0, maybe for some symmetry reason. So that's how we managed to discover the weak interactions, right? Because the weak interactions, absent the existence of the W's and Z's in the high energy theory, the low energy theory of just electrons, muons, and photons had a symmetry that independently conserved muon number and electron number. Okay? So the weak interactions are a leading thing, despite the fact they're tiny, the leading thing that breaks those individual symmetries and just conserves an overall individual lepton number with the neutrinos too. Or more famously these days, things like proton decay. Okay? So you look for some higher dimension operator, then the way you look for it is for a process for which the leading thing at low energies is 0. That's why, very naively, for things like this, it seems like you're not learning anything, because this is the most boring invariant operator there is, and this is just the square of it. Okay? So it's not breaking any symmetries, it's not doing anything. And indeed, if you're just a Euclidean quantum field theorist, that's true, but the world is not Euclidean, the world is Lorentzian, and we actually learn more about the structure of field theory by its Lorentzian consistency than you would naively imagine. That was, in a sense, the whole point of this old discussion. And what is the point? There is something that's kind of critical when you just are working with the two derivative theory. What is critical? What's critical is that signals propagate exactly on the light cone. Okay, so if you have, in just the standard two derivative theory, you know that signals propagate exactly on the light cone. And now, because they propagate exactly on the light cone, the higher dimension operators you could be sensitive to whether they push you inside or outside the light cone. Okay, so, and what you can do is turn on a background where d mu phi is equal to some constant, some k mu. For example, I could turn on a background where phi dot is equal to k. All right, so this is a perfectly decent solution of the classical equations of motion. I can make k arbitrarily tiny. Okay, so I can make k so small that you don't need to worry whether this is a good solution, uninfected by higher dimension even higher dimension operators and so on. So it could be an arbitrarily tiny background. In this background, we have not broken spatial translational invariance, so there's a good notion of speed of propagation of perturbations around this background. And so, but now it's pretty clear, you can do the exercise yourself, that if you perturb around this background, and you just look at the two derivative kinetic term for the perturbations around this background, the time and the space components will be treated differently because this background has broken Lorentz invariance. And depending on the sign of C, you will either go inside or outside the light cone. Okay, and so there is a correct sign for C that pushes you inside the light cone. Okay, so that's the long distance avatar of this problem. Now we can also discover this positivity. And something very similar is true for the Euler-Heisenberg Lagrangian. If you turn on f to the fourth terms, again, there's two of them, f to the fourth, ff dual squared. And once again, there are specific signs for both of them from the fact that, for instance, in a uniform electric or magnetic field background, the propagations are pushed inside the light cone. Now, there's another way of talking about this. First of all, whenever you're talking about higher dimension operators, it's always a little annoying when you use a Lagrangian because things are field redefinition dependent. Okay, so in this case, it's not so bad, but when you have lots and lots of operators, you can move things around by doing field redefinitions. The really invariant content of saying that we have this higher dimension operator is a statement about a 2-to-2 scattering amplitude. And so let me write down now we have an amplitude for 1, 2 to 3, 4 with scattering amplitude theta. We have the usual Mandelstam variables, P1 plus P2 squared. I'm going to imagine the external particles, well, I'll do it general. But let's say they all have the same mass, P2 plus P3 squared, P1 plus P3 squared. We have our usual S plus T plus U equals 4m squared. And also the relationship between these invariants, so things really only depend on S and T, and the relationship between these invariants and the scattering picture is that T is equal to S half minus 2m squared times cosine theta minus 1. Okay, so, okay, but of course, conventionally, as usual, we now think directly of the amplitude as a function of ST and U. So what does it mean that we have this higher dimension operator? It means that the low energy amplitude, if I look at the low energy amplitude, and I'm going to put a minus sign in front of the amplitude for the rest of these talks for reasons of convenience. The low energy amplitude is some constant times the leading thing that we get is from this C d phi to the 4. There are 4 derivatives there. So this is going to be something quadratic in S, T, and U. And so it's going to look like C times S squared plus T squared plus U squared if I just have a single scalar field with both symmetry. Okay? And so that's what most naively you take that operator, the Feynman rule associated with it would just give you that low energy amplitude. And now why can we say something about that sign C? Well, before saying anything very general and fancy, let's just imagine how we could get this effective theory, just for a second, okay? Where could this effective theory come from? What's the simplest theory you could imagine that gives you a massless scalar with a shift symmetry? Anybody? Goldstone boson, right? So just imagine you have a U1 you have a U1 theory with spontaneous symmetry breaking. just with a complex scalar field phi. Mexican hat potential. What do you have in the spectrum of that theory? You have a Goldstone boson. You have the radial mode, the Higgs, right? Except we're not gauging anything. And so when you integrate out that Higgs particle, you get this low energy. Interaction. So let's actually write down what the amplitude is in that case. And let's do it without doing any work. We don't have to think. Okay, why don't we have to think? Because, so there is some interaction between two Goldstones and a Higgs. So this is phi and the longitudinal mode. And so what could this give us? Okay, well, you just look at it. There's some coupling constant here. It's going to give us g squared. Okay, there's going to be a propagator, so I put a minus sign in front of the amplitude, so there's an m squared minus s. All right? Then I have the other channels. So g squared over m squared minus t plus g squared over m squared minus u. And now what I've done here so far is made sure that I have a scattering amplitude that has the property that has poles when either s, t, or u are equal to the mass of the particle. So that's correct, right? That's what the poles should be. And you'll see that on the residue of the pole, we'll come to this more systematically later, but on the residue of the pole, unitarity forces the amplitude to be given by the product of the two three-particle amplitudes that would make this intermediate state. Okay, so on this pole, the residue has to be given by that three-point amplitude multiplied by that three-point amplitude. And happily, because these are scalars, the three-point amplitudes are just numbers. Okay? So what I've done now is written down an amplitude that is guaranteed to give you the right answer on the poles. Okay? Now, we can do a little bit more. I also know these are Goldstones. So if I go to very low energies, I know that the amplitude has to go to 0. Right, because the Goldstones are derivatively coupled. And so you see that, I should say this a little more generally. This is guaranteed to give me the correct singularities that correspond to the production of the intermediate state. Apart from that, I could have some unknown contact interactions, which are just polynomials in S, T, and U. But in fact, we know a little bit about that polynomial. We know what the value of the polynomial is when S, T, and U are 0. Because when S, T, and U are 0, they need to give me 0 for the whole amplitude, right? And so in particular, a convenient way of doing this is to subtract from this a constant, which would be like 3g squared over m squared. Okay, if I subtract 3g squared over m squared, then I've gotten rid of the constant piece, right? And now you see, as I expand out to next order, I'm going to get a piece here that goes like S plus T plus U, which is 0 for the massless particles. And then the next term of the expansion will be S squared plus T squared plus U squared, exactly as we claimed. Okay? So after I subtract this constant, then the rest can just be some polynomial in S, T, and U in principle. And if I'm really matching to this underlying Higgs theory, then I know in the ultraviolet the amplitudes aren't growing. You know, I have a decent high energy theory here. So if I'm matching to that theory, then I even know that that polynomial is not there. Okay, so decency in the ultraviolet is what's controlling this behavior at infinity. So that's what got rid of this polynomial. And then these things are completely fixed by the behavior on the poles and something that we know about the low energy amplitude. But in any case, let's now, so that's without touching a Feynman diagram. We've just by knowing something in this very simple case about the pole structure of the amplitude, we can write down the answer. But now let's see why it is that we get positive coefficients. Now we get positive coefficients just when we expand in S, T, and U for totally obvious reasons when I do this expansion. So I expand this out in a geometric series. I get g squared over m squared, and then 1 plus s squared plus s cubed plus da, right? And I get the same thing for all of them. So that's why the coefficient of s squared has to be positive, right? In this example. And in fact, you see more than that. Not just the coefficient of s squared is positive, all of them are positive, because I'm just expanding this dumb propagator, right? I'm just expanding that the dumb propagator guarantees that they're all positive. Where is the positivity coming from here? So two things. First, that we have this pole structure. That's the most primitive physics of locality. In field theory, just at tree level. so it's coming from locality and unitarity. That's telling me that what I get is the product of the two coupling constants here, so that I get a g squared here, which is positive. Okay? So you see that it's locality and unitarity that are telling us that coefficient is positive.
Can I ask a question? So when you say impose unitarity, so therefore you do not, do you mean unitarity without referring to specific UV realization, or do you need to postulate the type of UV?
No. This is really something that, this is, well, in this example, I'm talking about a specific UV realization.
So you could have derived the positivity without using
I'm going to come to this in a second. That's right. Yeah, I just want to first see how it works in a specific example, then we'll say it more, then we'll say it more generally. But I want to emphasize something in relation to your question. It's not precisely the question you asked, but even without knowing anything about the UV, we know that these poles are there. And we know that the residues of those poles are positive in this model, right? So in other words, maybe in the UV I have the UV theory itself has higher dimension operators and, so whatever is going on in the UV, so long as I have these particles, I know these poles are present just at tree level, and I know that those coefficients are positive, independent of anything else. All right. So now let's quickly go through now the more general argument. I'm just reviewing this old story because we're going to basically mimic it and extend it, and then see some mathematically slightly surprising things about it. Okay, so a little bit more generally, let's look at, let's even simplify our life a little bit and look at the forward limit of the amplitude. So this is the forward limit. You saw from the formula that t is s half, in this case cos theta minus 1, that t goes to 0 means cos theta goes to 1, so that's the forward limit. In the forward limit, again, I have my amplitude now, it only depends on s, and so this is some constant s squared plus dot 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 at low energies. I'm still being slightly loose here for a reason that you'll see in a second. So let's go back to our previous example. Our previous example, if I now think about what's going on in the complex S-plane, the amplitude had a pole at s equals m squared. But apart from that, that was its only that was its only singularity, and down here it was just a polynomial. But now, you might know that, of course, when you can have more complicated theories, when you integrate out things at loop level, as just start anything beyond tree level, you also expect branch cuts. And so I'm sorry. And in fact, in this case, there are two poles at s squared, at m squared, at negative m squared, and this was from the s channel. This was from the u channel. Remember, u equals negative s negative t, which is just equal to negative s. Here at t equals 0, so we have a pole in the u channel. Okay, but you might expect that there's some kind of branch cuts here. So let's say we did something slightly more complicated. We integrated out a particle just at one loop, or at some number of loops. So we just integrated out massive particles. Then you would expect that you have branch cuts. Now, in absolute fullness of generality, you integrate out some massive particles. Just in that level of approximation, you would have this. You would have exactly this picture, where it would still be the amplitude would still be a polynomial at in S and T at low energies. Now, after you've done that, so whatever you did, you sort of integrated out some massive particle to get your effective d phi to the 4 interaction. Beyond that, of course, you will inevitably get these loops in the low energy theory too. Okay, so the full amplitude does not have the property that it's the full amplitude does not have the property that it's just naked and has it is purely a polynomial and then has a branch cut starting. It cannot have that property. Okay, so really there's a branch cut that goes all the way down to a 0. Okay, now in this talk I'm going to ignore this. In these lectures I'm going to ignore this. Well, I'll actually say a little bit about it at the very end. This is the physics of the running of these coupling constants. Okay, so these are higher dimension operators. Like every coupling constant, higher dimension operators run in the low energy effective theory. And so when we're going to be making statements about what the high, we're going to be making statements about sizes of higher dimension operators, and so these are going to be statements that are actually running statements. Okay, so correctly taking into account these extra cuts is going to be interpreted as taking whatever statements that I'm going to tell you about and thinking about them as statements that are valid even for the running couplings as you run to low energies. So I'm I'm going to avoid talking about that and only talk about things in the approximation where I've integrated out the heavy particles, and I'm ignoring the running of these couplings in the low energy theory. A formal justification for this is if you imagine that the particles that you're scattering have a weak coupling to whatever is out there in the UV. Doesn't mean the UV theory is weakly coupled. This could be photons coupled into QCD, okay? Or it could be gravity coupled to strings, okay? Anything where there's a weak coupling, either the alpha QED or the weak string coupling, in that approximation, the higher dimension operators are, so let's say we do a familiar situation to you guys. If we talk about higher dimension operators in string theory are suppressed by the string scale. The string scale is less than the Planck scale. So the higher dimension operators you get in the low energy theory are suppressed by a scale that's lower than the Planck scale. The running is proportional to G Newton. Okay, so the running effect, these extra cuts that go all the way down to low energies, are parametrically subdominant to the leading corrections that you get from integrating out the strings. And in fact, when people talk about matching to the low energy effective field theory and string theory, what they do is take a tree, in most cases take a tree string amplitude, just look at the contact pieces in the tree approximation, call those the higher dimension operators, and then if you really care about these tiny effects of what you get from running them to low energies, then you can run them in the low energy theory. But the running in the low energy theory has nothing to do with the unknown details of high energy physics. All right, anyway, this is just going to simplify my discussion, but so we have this kind of analytic structure. And furthermore, in the forward limit, well, we expect that the discontinuity of the amplitude around this branch cut is given by unitarity. I'm going to talk a lot more about that expectation later, but I'm just quickly summarizing an old story now. So we know that the discontinuity across this branch cut, the discontinuity of the amplitude across this branch cut is positive, is given by a cross section and is positive. Okay, so that's the physics of unitarity. Now we also know something else. We want this. We're looking for physics that has something to do with causality, and so there's a kind of a zeroth order question that we need to ask, which is how is causality reflected in the structure of scattering amplitudes? That's as I said, it's a big question that we're going to talk a little bit more in detail about in these lectures. But at zeroth order, the answer is that it's not naively obvious how it is. After all, an amplitude experiment, the LHC experimentalists wake up in the morning, they scatter the protons, they come back in the evening, and they see what the results of these scattering processes were. You make histograms and plots and cross-sections and so on. And how do you know from the information of what you measured at infinity that what happened inside can be given a local and causal description? Okay, it's not obvious. Really. You're not following. No one's going into the proton and seeing what's actually happening. Right? All of that is a story we tell as theorists to give a rational explanation for what the patterns are that the experimentalists see. So how is that fact about causality actually imprinted in the observable, which is the scattering amplitude. And the short answer is that we still don't know exactly to this day. We don't even know in perturbation theory exactly to this day. But roughly, it's in the fact that the scattering amplitude is analytic. Okay? It's not completely analytic. It can have branch cuts. It has, but it's not a wildly non-analytic function. It's basically an analytic function of the kinematical variables, and the causality is somehow reflected in the analytic structure. Now, this takes a lot of inspiration from a story that we're very familiar with, not for scattering amplitudes, but for two-point functions. Okay? And for two-point functions, we know we have the Challen-Layman representation. Okay? So if I have a two-point function, some sort of general two-point function, then I know that I can think of f of p squared as an integral. Actually, I won't be writing integrals. I'll be writing sums that are to be interpreted as integrals wherever appropriate. But a sum with some weights over, I have to put a minus sign, over m squared minus p squared. Okay? So, all right, so we have that representation, and so this is what's sort of telling you that, roughly you can think of any two-point function as a continuous exchange of a lot of particles with mass. That's putting in both the physics of locality and the structure of the propagator, as well as unitarity that tells you something about the positivity of rho if we're talking about something like O dagger O, right? So if this is if it's the Fourier transform of something that looks like O dagger O in momentum space. Okay, so for a two-point function, we know. For a two-point function, we know how causality, locality, unitarity, etc., are reflected in the analytic structure. This just tells you the two-point function indeed only has a cut that begins wherever the massive particles start. It could come all the way down to 0, but it has no other singularities anywhere else in the complex plane. All right, but if you try to mimic this for amplitudes, we don't know the answer, as I said, even to this day. If you open up these old books on the analytic S matrix, this was the elephant in the room, the monster at the heart of the S matrix program. The reason the S matrix program ultimately was doomed to fail is that people thought somehow they could, from first principles, somehow derive what the analytic structure of the S matrix was from some simple considerations of causality, locality, and so on. And they couldn't. So if you look at the books, they're cheating all the time, right? They look at Feynman diagrams. The whole point was to get rid of Feynman diagrams. And they say, oh, let's look at some Feynman diagrams. Okay. Oh, that's what it could be. Okay, fine. No, that's what the analytic properties are. Then they look at a more complicated Feynman. Oh, shit, it's not quite that. It's something slightly different, okay? So we don't know ahead of time what the analytic properties are. And in fact, as I will review a little bit, they're much more complicated than you would very naively expect. But there's hope for us, and for the purposes of working with vector field theory. After all, if we go to the forward limit, so first let me give some intuition, and then we'll see this in more detailed action. When we go to close to the forward limit of scattering amplitude, sort of literally in the forward limit, you see, a scattering amplitude looks like a 2-to-2 process, but in the limit where t is tiny, right, this is like essentially a two-point function. It's telling you about the amplitude for one particle sort of blasting through a soft background set up by the other. So you might think that while in general we don't know about the analytic structure of scattering amplitude, we should be able to say something about it in the forward limit. Okay, and and certainly for a 2-to-2 scattering, it indeed looks like a two-point function, so you think you might be able to say something about it. Okay, and so that's what tells us and that indeed ends up being true, and it's what tells us, if I go back to this picture literally in the forward limit, that this is what it looks like, and the discontinuity of the amplitude. So one thing is where the branch points are, that the branch points correspond to the production of particles, and then that the discontinuity across the amplitudes are going to be positive. There's another thing we learned, though, from this from the analogy with the two-point function, is that the high energy limit of the amplitude, if t goes to 0, or if we're a little bit more careful, if we just keep t fixed but small and negative, so it's in the physical region, then we expect that the high energy scattering amplitude, A of s, actually can't grow too much, and it's bounded by s to a power. This power can never get bigger than 2. It could be 1 or 0 or something else, but it can't get bigger than 2. And I'd be very happy to discuss this in more detail with anyone who's interested, but this is a subject that's been talked about now. I mean, it's an ancient subject, but it's been talked about now by string theorists a number of times. You could talk to either of these two guys in the front row, and they'll tell you all about it. But the intuition is very simple, that something that you remember from Jackson is that in order to, one of the reasons causality is so easy to talk about for two-point functions is that we know exactly what we're looking for in the time domain. We want something which has the property that it's 0 for t less than 0, and then it turns on for a t bigger than 0. And that implies some analytic properties for the Fourier transform. But part of those, part of the arguments requires being able to neglect contributions of contours at infinity. That in turn tells you that the phase in the Fourier transform of the two-point function has got to be bounded by an infinity. And when you translate that phase to what we compute relativistically from a 2 to 2 scattering amplitude, it tells you that the amplitude itself has got to be bounded by some power of s. That argument in general is just enough to tell you that it's bounded by some power. You just want to, without thinking at all, in order to get the number 2, you just have to work a tiny bit more in order to see that that's the case. Also, what saturates this? What saturates this is theories in the ultraviolet that have gravity. Okay, so and if you have an amplitude that has gravity at very high energies, in fact, goes like g Newton s squared over t. Okay, so that 1 over t is from the t-channel exchange of the massless graviton. This is if you have gravity. If you have Yang-Mills, then, and the guys that you're scattering are charged, then it only goes like s. The high energy amplitude just goes like g Yang-Mills squared s over t. Okay, and so here the power is 1 instead of 2. But the biggest it ever gets is 2 in its theories that have gravity in the ultraviolet. All right, so those are two things that we know about the amplitude. One, two things that we know from causality about the amplitude, that its analytic structure is simple. It only has branch cuts on the real axis. The discontinuities across the branch cut correspond to particle production, and that it's bounded, polynomially bounded, in fact bounded by s squared as s goes to infinity. And those two things are now enough, again, to make a statement about the behavior of the amplitude near 0. So let me just Cauchy's theorem then tells you that I can write negative a of now just s, remember this was t is 0, as, since it could in principle go as big as s squared at infinity, maybe there are two things that I don't know. These are called subtraction pieces, and we won't talk too much subtraction terms because I don't actually know what's happening at infinity. But the rest now has to look like a sum over m with some positive coefficients over m squared minus s. And again, the sum might be an integral. Okay? So Pm is a positive. And therefore, if I just expand this out in S, and if I have something in the U channel, it's m squared minus s. So if I have something that's ST symmetric, STU symmetric, just scattering a single particle, I have both of these terms. And so, so what I get are something with A0 and A1s, but then the rest, just by expanding this out, is going to be some positive coefficient, C2s squared plus C4s to the fourth plus C6s to the sixth, plus dot, dot, dot. And so I learn not just the coefficient of s squared is positive, but all of these coefficients are positive just by doing that expansion.
Nima?
Yes?
So are you including non-perturbative
Yep.
conditions as well?
Yep. Yep.
If you come back to the case of gravity, if you even look at the iconal sums,
Yes.
you get something that this is non-polynomial.
Oh, sorry. No, so I think you're talking about, well, there's an entirely different issue about how quickly the amplitude can die. But we're not talking about how quickly the amplitude can die. We're just talking about how quickly the amplitude can grow here.
Okay. Well, yeah, it must die at a certain rate.
That's right. It must. So that's a separate question, right?
It can't be non-polynomial when you look at it.
True, yeah. So there's some sense in which, especially black hole production, violates the standard notions of locality. Absolutely, but it's not showing up in this. It's not showing up in this argument. It shows up elsewhere. Yeah.
You're taking it into account, or you should say.
Well, I mean, I think it's true that the high energy amplitude does not grow faster than s squared. Okay.
Excuse me.
Yes.
So, why are those coefficients of s to the power 4 next to 0?
No, they're all positive. They're all positive.
Then how is it bounded by a square?
Oh, that's just what it is at low energies. Sorry. So you see, so this is what I learned from the whole argument, and now I'm just expanding this at low energies, right? I'm saying that I learned that the coefficients of the polynomials in the low energy expansion must all be a positive. I mean, a slightly more pretentious way of saying this is by doing a Cauchy integral, right? So I can do integral a of s over s to a big power. Use that to pick out the coefficient that I like, and then deform the contour around here, and conclude that the sums are positive. But you can also just more straightforwardly, that's what the whole amplitude looks like, is guaranteed to look like, which is a cool thing to know, right? And then if you now expand at low energies, you just trivially see that all these coefficients are positive. All right, so that's a review of the old story. And as you see, what you get from these arguments, from these amplitude arguments, these dispersive arguments, is strictly stronger than at least what we so far know how to get from, if you like, superluminality arguments in the low energy theory, right? So the first argument I told you about turning on a background, not being able to go outside the light cone, would just tell you that the coefficient of C2 should be not negative. Okay? In fact, it would be happy even if the coefficient of C2 was 0, and it doesn't tell you anything about the higher coefficients. Right? So strictly, the argument about you have the d phi to the 4, you turn on a background, only tells you that the coefficient of d phi to the 4th can't be negative. We're learning more. We're learning that it has to be strictly positive in an interacting theory, okay? And that not only it, but in the approximation, where I forget about the running of the operators and all of that stuff, in the approximation we talked about, not just the d phi to the 4, but all the higher dimension operators are in fact positive. All these higher dimension operators are positive. Okay, so that was the old story, and we were sort of inspired to go back to look at it again from some of the qualitative things I mentioned before that we've seen over the past 10 years, sort of surprising kinds of positivity, nonlinear positivities, sort of positivities involving matrices and their determinants being positive, and things that are not just they're sort of somewhat more subtle and interesting positivities. So we decided to go back to see whether anything like that was going on here. And indeed there is, and that's what I want to tell you about. But before I do that, let me actually tell you where we're going. Okay, so everything that I talked about there was in the forward limit. So the first thing I want to do in the first part of these, now the proper part of these lectures, is talk about what the amplitude looks like as a function of s in the general s-plane. Again, when t is fixed and negative and small compared to the thresholds of the particles that we're integrating out. And so this is the first thing that I want to say. So there are the subtraction pieces. So there's some a0 of t plus a1 of ts. I don't care about these. I won't keep writing them down anymore. But there's an extension of what we talked about before, which looks like this. It again looks as if we have a whole bunch of particles that we're integrating out at tree level. It would be that, in which case the sum would literally be a sum, but in general, if we have loops, whatever's going on, you have the same thing with the sum being an integral. So we have the propagator. So to sum over a spectrum, this curly S is a spectrum of spins. So this is saying that at every mass level m, we actually can exchange particles of also of arbitrary spin. And so up here, I'm going to have some positive numbers now that correspond to the, if you like, beforehand these numbers correspond to the probability of, or the cross-section for producing everything at s equals m squared. Now it's going to have the same thing, but also know something about the spin of the intermediate state. Okay. All right, so where these objects, these GS's, are the Lejeune polynomials if you're in 3 dimensions. So this looks like the partial wave expansion. And in general dimensions, they're known as Gegenbauer polynomials. Okay, so you might recognize this as cos theta when s is equal to m squared. Okay, so this is saying that we can think of any amplitude, no matter what, as a, let me put this up here. As if we're integrating out particles of general mass and general spin. I'll explain where all this comes from in a second. I just want to plus the U channel. U channel means exactly the same thing, so let me be explicit. Plus exactly the same PM of S, GS 1 plus 2t over m squared over U. So m squared minus s minus t, which is U. Okay, and I should also say, what scattering process are we talking about? We're talking about not the most general scattering process in the world, but a process where I have AB goes to AB. Okay, so the initial and final states are exactly the same, so that should be the ones you would expect you can make positivity statements about, familiar with the optical theorem and so on. We're just generalizing all those old statements. Okay. All right, and for simplicity here, I'm talking about scalars on the outside. I'll say a little bit about what happens for arbitrary spin. Okay, so we're going to argue, and I'm going to show why this representation is true, why we can represent things in this way. But then we want to see what are the consequences of 2 positivities here. 1, these probabilities are positive. 2, these mass squareds are positive. So as promised, we have the positivity of probability and the positivity of energy, okay, are 2 things that are positive, and they're going to tell us a lot about the low energy expansion of this amplitude. Now we're going to take this amplitude and expand in a power series in S and T and extract the low energy coefficients. All right, so we want to say something about that infinite tower of operators. So let me just introduce some notation and the cast of characters for the rest of the talk. So if I take this thing Now, at low energies, so in other words, where I'm just doing the polynomial expansion here, the Taylor expansion, I'm sorry, this is just some coefficients that we can just call A, P, Q, S to the P, T to the Q. And I will also find it convenient to sometimes write this as a sum over D and Q, where D keeps track of the overall dimensionality of this coupling. So A, D, Q, S to the D minus Q, T to the Q. So capital D, again, just counts the overall scale of the coupling constant. Okay? So this is the set of objects I want to make statements about. Okay, so that's what we're going to be studying for the rest of these lectures, is what can we say about this infinite set of coefficients A, D, Q. So let me just list them here. So I have A00, A10, A11, A20, A21, A22, 30, 31, 32, 33, and so on. Okay, so there's this whole matrix of these guys. Okay? And I want to say something about them. And first, there's the business about the subtractions. I'm not going to keep talking about the subtractions over and over again. What the subtractions do is they tell you that anything that has 0 or 1 power of s, I can't control. Okay, because that has to do with the subtraction pieces, so I have to begin with s squared and higher. Okay? Just so I don't say that over and over again, I'm going to ignore that fact, and we're just going to treat this whole table as just coming from the sum that I wrote down where I ignore the subtraction pieces. Whenever you want to use it, you just have to remember that everything begins with s squared and a higher. Okay, just so it's less annoying to keep saying it over and over again. Okay, but what do we know already then? What we know already is that many of these coefficients are positive. For example, we concluded that A20 is positive, A40 is positive, and so on. Right? That's what we decided from our previous discussion. That was a coefficient of s squared, of s to the fourth, and so on. Okay, but even before I tell you anything fancy, you surely have a feeling that you should be able to say much, much more about the structure of higher dimension operators. First of all, you know that, or you have the feeling that if the dimension 6 operators beyond the standard model are suppressed by a TeV, were we so lucky, probably the dimension 8 operators aren't suppressed by 1,000,000 TeV, right? So there should be some kind of correlation between the scales of all the different higher dimension operators, right? Now, you might think, well, maybe that's just what happens naturally. Maybe you could fine-tune or something and arrange it so that the dimension 6 operator is suppressed by TeV and the dimension 8 operator is suppressed by 1,000,000 TeV. Okay? That's why in all these questions about what is or isn't impossible in effective field theory or the swampland or whatever, generally, some kind of precision is really important. Okay? Because the whole point is to distinguish between what's kind of natural in order 1 and what's totally precise and either can or can't be done, even with any amount of tuning. Right? So that's what we're after. So very precise statements. So you might naturally think that all the scales are related, but the question is there something precise that relates them to each other? And that's exactly what we're going to see. Okay? In fact, everything in these rows, okay, if I take any one of these rows, like the top row, we're going to find an infinite number of nonlinear consistency, nonlinear inequalities that are satisfied by different guys in these rows. Okay. I'll give you an example in a moment. Well, let me give you an example right now, just so you get an idea for where this is coming from. Let me just slightly simplify my life. Let's go back to t equals 0, that thing that we did before, and let me just keep the S channel, okay, just so I know U channel. Again, just to slightly simplify the equations I write, just so you get the point. So I have something that looks like negative A of S is the sum of Pm over m squared minus S. Okay, and so this is the sum of Pm over m squared to the q plus 1, S to the q. Okay, and so I learn immediately, in this case, what are all these coefficients? So, okay, so this, on the other hand, is sum of some, I don't know, AD, S to the D. And so I learn that A0, A1, A2, blah, 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 is equal to the sum of Pm over m squared times 1 over m squared, 1 over m to the 4th, blah, blah, blah. Okay? So all I've done is just write down the formula for the coefficient of s to the d, just in this expansion. Okay? I don't know what these probabilities are Pm. I don't know what the m squareds are, but I know that the Pms are positive, and I know the m squareds are positive. So the question is, what can I say about these coefficients given that information, and that information alone? One thing I can say is that they're all positive. That's the sort of dumb thing that we've said already. Okay, but it's completely obvious there's vastly more than you can say. And, and before we get to it more fancily, I invite you, while you're skiing or right now in your head, because it's that simple, to use the Cauchy-Schwarz inequality to show that A0, A2 minus A1 squared is strictly positive.
Can I
Yes.
ask? So can I ask the same question I asked before? So
yes.
In this particular case,
yes.
again, is this quadratic relation consequence of this particular assumption about?
No, there's no assumptions at all. There's no assumptions about.
So can you derive this thoroughly?
That's what I'm going to show you. That's what we're going to. So I'm just giving the structure of what we're going to talk about.
This is a motivation,
right.
and there is a separate
so that formula for the structure of the amplitude is completely universal. Okay, and now we're going to when I take that formula and I expand it at low energies, these are the consequences. So there are two things. One is to show that that the amplitude has that representation, the one that I showed you. Okay, the sum is in general an integral. We have a branch cut and so on. We don't have poles, but it doesn't matter. So that's the first thing, and that's what we're going to spend. That's the general physics education part of the lectures. Then there's some just purely mathematical part to explore some hidden positive properties of A, the propagator 1 over s minus m squared, and B, the Gegenbauer polynomials. Okay? And so there's something slightly hidden positive in those two things that actually allows us to say an enormous amount about the coefficients of these higher dimensional.
Thank you.
Okay. All right, but anyway, this is just a little math problem. Okay, just use the Cauchy-Schwarz inequality to show this. So we learn much more than just that A0, all these A's are positive. As promised, there's a nonlinear relation between them. Okay, which says that the product of two operators of smaller and bigger dimension is bigger than the square of one of the intermediate dimension. So, okay, so that's one indication that there's a little bit more, but there's something else that I can say too. Let's go back again to my big table. So again, I had these A00, A10, A11, A20, A21, A22. So we've seen that in these rows, there are interesting nonlinear conditions. Now let's look at the columns. Okay, the columns are also interesting. These are like a whole bunch of operators of the same units, right? And so now here you would expect that if you have a bunch of dimension 8 operators, you shouldn't be able to make one of them 10,000 times bigger than the other one. Okay, so you would also expect there to be some relations between operators of the same dimensions. Okay? And there are also relations like that. Those relations follow from, those relations, clearly, that has to do with the expansion in T, right? And that's all going to have to do with looking at these Gegenbauer polynomials, 1 plus 2t over m squared. That's how they show up. So I expand this out in T. This is some, for any spin, this is going to be some GS, some sum over Q, GSQ this thing to the q, just doing the Taylor expansion. And therefore, if I'm going to be able to say something interesting about the t dependence, I need to be able to say something interesting about these coefficients. Okay, so about these Taylor expansion coefficients of the Gegenbauer polynomials. And I'm going to tell you all about the Gegenbauer polynomials in a second. I'm not assuming that you know about them ahead of time, but just so you have some idea of the kind of thing that we'll be seeing. If I look, you're even familiar from ordinary Lejeune polynomials that when the spin is equal to 0, they're equal to 1. When the spin equals 1, they're equal to cos theta. When the spin equals 2, in d dimensions, it's like d cos squared theta minus 1 if I'm in d spatial dimensions, and so on. Or they're proportional. I'm not writing down the overall normalizations. But anyway, so if I look at these Taylor coefficients, so here is for spin equals 0, spin equals 1, spin equals 2. I'm just expanding these polynomials around this forward limit. See, this is around the limit where t equals 0 when cos theta goes to 1. So something interesting is happening in the neighborhood of the forward limit. So here is the 0th Taylor coefficient, the first Taylor coefficient, second Taylor coefficient, and so on. Now, this is what this guy looks like. I'm just here I'm working in 3 spatial dimensions. These are just Lejeune polynomials. And all I want to point out is that the usual statements that we're used to making have to do with the fact that the top row here is positive. That in the forward limit, as t goes to 0, that these Lejeune polynomials are positive. And that, again, is famous from applications in the optical theorem and all sorts of other things. So the fact that the top row is positive is the obvious positivity property of these orthogonal polynomials. But when you stare at these guys, they have more things that are positive. For example, all of the Taylor coefficients are individually positive too. That's curious. Ancient observed fact. Of course, people like André Martin use this fact to say lots of interesting things away from the forward limit of scattering amplitudes already in the 1960s. But that's already somewhat, maybe not familiar to everyone. Everyone in one way or another knows the top row is positive. The fact that all the other ones are positive is, well, known to anyone who's looked at it for half an hour, but probably most of you haven't looked at it for half an hour. However, there's something even beyond that, and we'll see the relevance of this fact probably tomorrow, is that all of these statements are actually special cases of a more general one. That in fact, all of the minors of this matrix are positive. You calculate any determinant, you take any rows and any columns of this matrix, all the minors are positive. That is actually a new fact. That's a fact that, as far as I know, is not known to the mathematicians, but is part of this general story of playing with matrices with their positive determinants and so on. That this a kind of story we've seen over and over again in the context of amplitudes and polytopes and all that kind of stuff. Okay? So as you'll see, that's the hidden positivity of, by the way, in the case of 2 spatial dimensions where these Lejeune polynomials are just cosines, this fact wasn't known to Chebyshev in the 1850s. Okay? But the more general fact for general Gegenbauer polynomials was, as far as I know, not known. And as we'll see, that fact is going to have an implication. It's going to tell us that all the things of the same units, all those objects, you see, they all have the same units, so it's natural to only talk about their ratios. And in particular, you can think of them as points in a projective space, because you only define all the columns up to their overall scale. And what we're going to learn is that all those numbers are actually live inside specific polytopes. They live inside specific shapes, specific polytopes. Not just that they're positive, which just says they're on the right side of some wall, but they live in the very specific shapes. Okay, and all of those statements, the nonlinear statement, as well as these sort of polytopal ones, are actually are contained in a much larger nonlinear statement that, if I have time, I'll tell you something about. Anyway, so that's our plan. Oh, sorry, I'm done for the first lecture. So my plan for the rest of the lectures is, in the next lecture, probably it'll take us the entire lecture to essentially talk about where that representation of the amplitude comes from. Okay? How do I know I can write the amplitude in that way? What are these Gegenbauer polynomials? How do I know I can write the amplitude in that way? We'll talk about what's known about the general structure of 4-point scattering amplitudes. These beautiful old things, which again were probably talked about in this room in every school in the 1960s, but maybe aren't standard fair and field theory courses. We'll talk about Landau equations, how we know about the structure of scattering amplitude singularities in general, anomalous thresholds, all these scary things that are out there in the big world of possible analytic structure of scattering amplitudes, but which we can ignore in the limit that we care. Okay, so that's so I could not tell you about them, but I want to tell you a little about them anyway, just so you see the sort of monsters that are out there. And so that's what we'll do in the next lecture. So the next lecture will all be about the sort of physics and the sort of kinematics of that representation for amplitudes. And then tomorrow we'll revert to some very simple mathematics. And I'll tell you first in general how to think about a large class of problems of this character where an object of interest is expressed as a positive sum of a set of basis objects. Those questions are all naturally phrased in the language of projective polytopes. And there's if you take nothing else from those lectures tomorrow, every time you run into such a question in your life, I want you to do what you learned tomorrow, okay? Because it'll make it easier for you, it'll make it easier for me, it'll make it easier for everyone. If when you run into a positive problem, you treat it the way I'll explain tomorrow. So I'll tell you about how to do it in complete generality, but then we'll focus on the actual problems that are handed to us by physics, which have very, very special character to them. We don't run into random geometric objects, we run into very special, classic, famous ones, okay? Which are very well understood by mathematicians and have all sorts of beautiful structure, cyclic polytopes, convex halls of moment curves, and those notions will be the ones that control the structure of effective field theory. All right, thanks a lot.